The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to Coffee with Caleffi, the season finale. Here we are wrapping up 2017, and we've got a barn buster of a presentation, and we're going to get right into it. We've got a lot of content to cover, and we've got a contest at the end, so it's going to be a fun presentation. So what do you got there, Paul, for some slides? Now, these here we send out there, sometimes your local authority will accept those as credit hours. That's all we can offer. We don't proctor this or anything, so we send out that certificate for you to use as you please. And hydronics,
Sorry,
number 22 will be coming out in, we'll be mailing in January. We've got a slide of that coming up a little bit later, but get on the mailing list if you're not on it. Let us know how we can help you, and also let us know of topics that you would like us to cover. And that brings us to Paul's our presenter today. He's a friend of the industry, a friend of mine. He's got a lot of experience. He's got contracting experience. He was involved with some award-winning jobs when he was with the RPA early on. I think he's been with Lochinvar, maybe 8 years now as their technical trainer and director. So I can't think of a better person for this topic. So as you can imagine, we've got a lot to talk about. We're not going to get to every specific thing about every category of ways to heat hot water today, but Paul's done a really fine job, so I'm going to turn it over to him.
All right. Well, thank you, Bob. As you can see with this skeleton frame, this agenda, this is a very broad topic, and appreciate the opportunity today and having everybody along. But we're going to move along at a pretty good clip. We're going to put in a bunch of questions as we go. And as this is such a broad topic, my goal really is to be transparent, but to give you as much granular information as you can. So this really is intended to be a side-by-side comparison. I don't want this to be a cloaked sales meeting, so we're going to keep this framework very tight-knit, and we'll get right into it. Some of the best advice I was ever given in my career was always talk about what it is and how it works. And we're going to compare tank-type under-fired heater versus tankless water heaters, and then Combi boilers, which both provide space heating and domestic water. But right out of the gate, a tank-type under-fired heater, it isn't a staple in our industry here in the U.S. You'll see on that right-hand side right here, this dip tube, all of our cold water comes in here, and it is just a wide part of the pipe. We've got an under-fired burner, and in this center part right here, we have a baffle slowing down those flue products so that we transfer as many BTUs as possible. So not a lot of working parts here, very simple, very modest pressure drop through them, and tank type heating is very simple and straightforward. One of the questions was, well, are you going to talk about heat pump water heaters? Well, I sure can. Heat pump water heaters are emerging. They're a little bit higher priced, and they have very specific parameters they need to work. And in general, they work much like the refrigeration process in reverse. So instead of rejecting heat, we're absorbing heat and then transferring that into the water. And we aren't really going to be talking about this in the side-by-side comparison today, but we are going to focus on tank type, tankless, and then combis. And tankless water heaters, it's a singular chassis. It's got a burner. There's a lot of different makes and models. Some of them are condensing, some of them are non-condensing, but they operate based on a flow rate. And then once that flow rate actuates the unit to fire and says, I need heat, I've got a call, let's send some hot water downstream. These are, even though it's a fairly small chassis, there's a fair amount of sophistication in there. And we'll talk about how to control them and how these actually operate. But one of the things that you will hear me talk about today repeatedly is that the higher the temperature rise, the lower the flow rate. And we'll talk about that in greater detail here moving forward. But it is essentially, we have a heat exchanger. The potable water directly goes into the heat exchanger where it's heated by the flame. We transfer that into the water, and it goes right out to the fixture. So it is a direct fired appliance. And again, this particular model, we can talk about a modulating gas valve, but some of these truly modulate and some of these have staged burners. So when we say a tankless heater, that does cover a very wide spectrum, and we'll talk about specifically some specific units here in just a few minutes. And then onto the Combi. As the name suggests, a combination boiler provides both space heating and domestic water production. So in this little iteration here, we're just showing this animation that shows on a call for heat and a space heating load, the boiler turns on, the internal boiler pump will handle that flow. In this instance, we have it on closely spaced tees for proper primary, secondary operation, but that is how it will work as it pertains to responding to a space heating call. Now, internal to the boiler, you will see this little brace plate exchanger and these brass valves right here, and there is a two-position actuator. And this two-position actuator, when it actually calls for heat, you'll see that actuator spring move over to the left there. And as that system fluid comes back from the space heating side, the system, it will go up through the boiler via its own circulator. We'll pick up the BTUs in the combustion process, and then we'll allow that flow to be directed right back out to that space heating load. So that is how the operation looks, or how it performs on the space heating side. Now on the Combi, on the domestic side, we will actuate a call for heat, or excuse me, not call for heat, but a call for domestic based on a flow rate of a minimum of 0.32 GPM. So even a partially open lab faucet or kitchen faucet is going to tell the unit we need heat, and it's going to actuate flow. And then that same brace plate exchanger, that two-position actuator is going to go back to the default position. And now instead of allowing flow out to the space heating side, it is going to only allow flow through the upper half of that brace plate exchanger. So the boiler flow then becomes very circular. It goes up through the heat exchanger, down through the brace plate heat exchanger that you see there, and we're transferring BTUs into the potable water, which then is flowing through the bottom side of that brace plate exchanger. So this is not a direct fired appliance. The potable water never touches that flame or sees a flame. And we'll talk about some of the added benefits of that as well. So these three different devices, they work in completely different manners. Now on to applications, and you'll see the industry really is shifting to storing water or producing water at a higher temperature so that we can stave off Legionella issues. And if you're not familiar with Legionella, the bacteria, the higher we store water, the quicker that Legionella will die. If we store water at 140 degrees, 32 minutes later, that bacteria will die. And the magic number is instantaneously at 158 degrees, that Legionella bacteria will no longer continue to live. So for the sake of today, we are only going to show, or we're going to illustrate, the use of a mixing valve, not only on a tank, but on the tankless and as on the potable side of the Combi as well. And there's another reason why I'm going to illustrate this, because some of the emerging technologies out there and the components that are now available, that might play to our strengths as it pertains to recirculation, but I don't want to get ahead of myself here. So we talked about how they work, but now we're going to talk specifically about sizing. And the elephant in the room for us as it pertains to a side-by-side comparison is we're just going to pick this model right here. It is probably the most prevalent model out there, 40,000 BTUs, tank type under-fired unit, 40,000 BTUs, 40 gallons of storage. And with that, so that we can compare this in an apples or a side-by-side comparison, we are going to go to that first hour rating, and that is how we size a water heater. With the storage and the BTUs on board, that unit will produce 78 gallons per hour. So that's just a baseline of what we're going to move forward as, 78 gallons per hour. Now on to tankless. Tankless is sized by peak flow rate. So we need to know what the worst case scenario is. What is that maximum flow rate for that peak load that we've got to sustain? And for today, we're going to just not condensing. So it's 199,000 BTUs, a lot more BTUs there, and it's going to heat a fair amount of water. It doesn't hold a lot of water, but we're going to use a large number of BTUs to heat that flow. And at this particular model, at a 77-degree rise, which is kind of what the industry defaults to, a 4.2 GPM flow rate will produce 252 gallons per hour. Now that again is in contrast to the tank type heater that was 78 gallons per hour. So again, going back to the narrative, in a side-by-side comparison, we have a tank type under-fired heater that is only 40,000 BTUs, but we're banking on that storage capacity of those 40 gallons. Whereas a tankless, again, no storage involved, it has to produce those BTUs on the fly, so 252 gallons per hour comparatively.
Hey, Paul, a rule of thumb that somebody shared with me here recently when I was out doing some training, they said it takes about 50,000 BTU to do 1 gallon per minute at about a 75 to 77 degree temperature rise. So that's why you see usually about the smallest tankless or combi you're going to see is going to be about 110,000 BTU input, and that gets you right at that little over 2 gallon per minute, instant flow rate.
That's great feedback. That's a really good number to use in terms of, ballpark numbers, 50,000 BTUs per GPM of temperature rise. The thing that is true with tankless, and again, I use the word generically because there's a lot of different types and styles of tankless heaters, but the higher the temperature rise, the lower the flow rate. So down here in this schedule right here, we're looking at saying we have a 40-degree temperature rise. The water's coming in at, let's say, 35 degrees. And if we raise it 40 degrees to a 75-degree exiting water temperature, I'm going to get a flow rate of 8 GPM. But as we travel down this scale right here on this axis, the higher the temperature rise, the lower the flow rate. And in several units, there is this device here called a bypass and flow adjustment valve that will sacrifice flow to maintain set point. So in short, if you have a lap faucet open or a shower faucet open, it's going to want to meet set point at your delivered water temperature. If you want to deliver 110 degree water, it will deliver 110 degree water unless it's not able to keep up with that appropriate temperature rise. It will limit the flow through this device so that it can maintain set point. So again, the higher the temperature rise, the lower the flow rate. And we'll talk about this in detail as it pertains to commercial here on my next slide. As it pertains to sizing criteria, there's a lot of things to be looking at as it pertains to sizing a tankless heater, especially what are, my max flow rate of all the showers if they were running, or if this is an empty nester, if I'm got a load going of laundry and a shower or laundry and kitchen, what is that going to do to my max flow? So really what you're looking at is defining what that user, that flow rate and the load profile will look specific to that user. But again, there's a lot of disparity between the criteria for residential versus the criteria for commercial heating. So that turns into a completely different animal at that point. And this drove a very big question from a lot of you out there. And what is that line of demarcation? If I'm going to do a commercial application, how many heaters then become cost prohibitive? Because I don't have any storage, I need the greater number of BTUs and the greater GPM capacity because there is no storage. But again, we go back to that same narrative of the higher the temperature rise, the lower the flow rate. Here on this blue line, I'm showing a 40-degree entering water temperature. And again, down this scale here, down this axis, the higher the temperature rise, if I want to deliver 135 degrees, that's going to limit my flow rate. And that would then drive a larger number of units. Now this next slide, this addresses that question. How many tankless units should I consider before moving up to traditional sizing methods that include storage? And this is a very subjective question. This was one that came from a pre-submitted question. And I did some legwork as it pertains to what is that best answer. And I don't think there's a single correct answer here. But anecdotally, I solicited information from a lot of contractors in Texas and in California. And in a commercial application, a lot of them would say, if it takes more than 6 tankless water heaters, I would pretty much move up to a traditional forced circulation system with storage. So what does that actually mean? Well, instead of a larger number of units 4 to 6 to 8 to 10 tankless heaters. You can do that if you choose, but there is a line of demarcation that basically says, look at your load profile. Now, down on this bottom right-hand corner right here, this is called a Hunter curve, and it is a load profile for an elementary school. If you think about the water usage patterns of a elementary school, there are no large banks of showers. There's generally only a kitchen load right after that lunch hour. So that will give us our peak demand. And that is very simple to size for with tankless water heaters, because we can meet that modest GPM capacity. We don't really need storage. But then when we move up to something like a hotel, this would be a load profile or Hunter curve for a hotel. A large number of people, the bulk of that peak load is going to be in the morning between, let's say, 6 and 9 a.m., where not only do we have to bank on the BTUs of that heater, but the additional storage as well. So in this instance, maybe we have 250,000 BTU heaters and 200-gallon storage tanks, whereas without storage, we might need 12 to 15 to 18 tankless heaters because we have to size for that peak recovery in GPM. So we've been doing this a very long time. We do forced circulation with storage, and it does meet the need. But again, in this iteration, we can talk about a large number of tankless heaters then being required. But then that number of tankless heaters would then need to be serviced every year. We have to deal with the venting requirements of 12 to 18 to 15 heaters, gas piping, and so on. So we need to, again, keep it back to the basics of a first cost. Is my first cost advantage installing 12 to 15 heaters with the venting and gas piping and then servicing and maintaining them every year? Or would 2 larger tanks and, as it were, storage and smaller heaters be more appropriate? Would that be a better economy of scale, if you will? So these are the questions at hand. And I'm sure at the end of this presentation, that will generate quite a few more questions, so I'm glad to address it further. Now on to Combi heaters, and as the name applies, we have a couple things at work here. We have the potable side, and with a 199,000 BTU heater, we can divert flow from the space heating side that you saw in that illustration, that animation, and we can supply up to 4.8 GPM at a 77-degree rise. We can do that all day long. So that 4.8 GPM at a 77-degree rise gives us 288 gallons per hour. And again, that is in contrast to the 252 gallons per hour of the tankless heater and 78 gallons per hour for that first hour recovery for the tank type heater. And again, we're talking about a 199,000 BTU boiler and water heater versus a 199,000 BTU tankless versus 40,000 BTUs for the tank type. So as a true side-by-side comparison, the largest BTU capacity, or rather the largest GPM production for domestic water, would go to the Combi. And we'll revisit this slide when we start talking about the trade-offs, and we'll sum it all up in that as we move forward. Now, piping is very straightforward. With a tank type water heater, if we're just doing standard non-mixing, it becomes very easy to pipe. But even a simplified mixing valve, a hot-cold mix principle, if you will, very, very straightforward. I think most of you would then adjust your mixing valve with a thermometer saying, I want to deliver 110-degree delivered water temperature. So we might choose to store at that 140-degree temperature, knowing that in 32 minutes, we're going to stave off any Legionella issues. That's very practical at that point. But I like showing the mixing valve especially because some of these new components that are out there in the industry, I think, have the ability to groom and shape what we do as an industry. And Bob, you can jump in and describe this, but this is new from Caleffi. I'm only seeing it now in the industry starting to saturate, that it is a built-in mixing valve that offers a lot of value. So we're doing a hot-cold mix principle, but it will greatly simplify piping, I believe. Anything to add there, Bob?
Yeah, that's a new, again, not a product specific, but that's a what we call our tank mixer kit, and it comes just as you see it there with an angle version of a thermostatic mixing valve, which is nice, so you don't have to make that big curlicue on your piping to cross over to the other side, where we've got that cross T that you can also bring your recirculation right into that. So it's just really quick and simple. The union connections, you screw it on your two connections coming out of the tank, and I think we have some pictures coming up of that, and set the temperature you want, and away you go. It's a really nice application for that, and there it is in a tankless.
I think it's a great application for the tankless as well as the Combi. One of the questions that was generated was, and it's kind of in contrast to how we heat water in the United States, the question I've heard most of Europe and the rest of the world heat with tankless. Well, in Europe, that's a dominant hydronic market, and you'll see a lot of boilers and indirect heaters in Europe, at least in Western Europe. In the United States, the opposite is true, where the dominant source of heat and hot water, or rather hot water in the US, is a tank type under-fired heater. So to answer this question directly, in the rest of the world, yes, a tankless water heater is a really dominant factor in Asia and Eastern Europe as well. So tankless water heaters, they're here to stay. They absolutely are. Another question we received was, can a hot water recirculating system be used with a tankless water heater? And absolutely, we have it in our manuals. We've gone to great lengths to illustrate this, but there's a couple caveats. To heat water successfully and to do recirculation with especially a tankless, there are some parameters, and those parameters are that we want to see a minimum flow rate of 2 GPM so that we can properly actuate flow, and we want to see a maximum of 4 GPM. In that recirculation circulator, we also want to see the benefit of an aquastat and a timer. I think that will, in the definition in the manual as it's laid out, give us very good reliability for circulating hot water at given times of the day. And we'll address this a little more fully here in a minute. This is, again, a great resource. If you don't have this Hydronics 21 manual, I refer to this a great deal because navigating proper recirculation piping can be a little tricky. Just the misplacement or having one check valve misplaced can really leave you scratching your head. So here I'm showing 2 tankless heaters. Maybe this is a large residential application. Maybe it's a light commercial application. Yes, we can do recirculation with tankless water heaters. And this, again, is a supplemental PDF that we have on our equipment. But what I really liked about that tankless mixing unit was that it greatly simplifies recirculation. You bring it right into the side of that unit, as Bob indicated previously. And to me, that is a big value. Reduced man hours of piping and fittings. I think it is just a really dynamic way to do your recirculation from here on out, now that this type of item is available. So then on the potable side of a Combi, in terms of piping, we've got a lot going on here. But if you break it down into modules, it becomes very simple. Over here, here's my potable that you saw earlier, my hot cold mix principle, so potable water actuating flow, hot water coming out to the mix, I'm mixing my cold water back in, and here's my delivered water temperature to the potable side. So the duality of a Combi boiler is that I'm also providing space heat. Here, I'm illustrating a primary secondary operation, and what that means in layman's terms is flow in my system loop over here is not going to induce flow in my boiler loop. And what is true about this Combi boiler is behind that jacket, there is a circulator that is included with this appliance. It's pre-built in, it comes with unions, so flow in my dedicated boiler loop here does not induce flow in my system loop. And this is shown with a SEP4, a 4-in-1 separator. And it has the benefit of being, provide some duality and redundancy because it is not just hydraulic separation, it is air separation. There's media in there that would then provide dirt separation. And down below here, there's a magnet that also gives me magnetic separation. So these are very popular in the industry right now, especially if you're doing primary, secondary. If you've got a flow rate in your system that is greater than your boiler is capable of, maybe the boiler is sized sufficiently for BTUs, but I've got a flow rate and a narrower delta T in my system, hydraulic separation would then be in your future. So closely spaced T's, hydraulic separators, low loss headers, these would all be applicable. So if you break it down into modules, I've got my space heating load, I've got my boiler loop, and I've got my domestic, and it becomes very simple. As a reminder, my expansion tank location in this is very, very important. And wherever my expansion tank ties in, that is my point of no pressure change. So the rule of thumb in our industry is that circulator needs to pump away from that point of no pressure change. So as long as my circulator, at the suction side of my circulator is drawing from where that expansion tank is located, we meet those requirements of pumping away from the point of no pressure change. So that's true primary, secondary. But with these appliances, this is a fire tube heat exchanger. And this fire tube heat exchanger has a lot of benefit to it. Not only does it hold more system fluid, it has a very nominal pressure drop, a very low pressure drop. So in this instance, this circulator that is on board with the boiler, the appliance, we can full flow. So instead of requiring primary, secondary operation with a dedicated system pump, we can use the circulator that is on board with this appliance to drive flow, not only through the boiler, but through the system as well. And that is a very, very big benefit from a first cost standpoint. The gotcha moment would be that we have to look at what the flow and head characteristics are of this circulator to match that of our load. But it is very much applicable to full flow these now. You're seeing the industry gravitate to full flow systems, provided we can meet the flow and total dynamic head of that space heating load. Bit wordy there, but I think you get the idea. So that same instance, can a hot water recirculating system be used with the Combi? Absolutely, for certain. That's again, we would like to see that with a min and max flow rates, as well as a timer and an aquastat. And we'll talk about another feature of a Combi as well. This picture up here on the right came to us from Nate White Plumbing and Heating and Kenai. It's a Combi boiler with that mixing valve, and Nathan usually stays pretty cutting edge. He's on top of it, so we've always appreciated his install pictures as well. Tip of the hat to you, Nathan, if you're out there. So there's the bottom side of that. Again, greatly simplifies that piping. But one of the questions that came to us was, and this is a very legitimate question, since there's hot water in the pipes, they lose heat, even if they're insulated. How do you get full temperature water at sinks and showers, you know, out in the load, as it were, at the fixtures? This person was especially concerned about this with tankless water heaters. And again, this is true with tankless as well as Combis. And that's an absolutely true statement and a true concern. We call that a cold water sandwich. So if you think about it, what the author of that question is saying is, unless I have flow through this unit, I'm not delivering hot water out to that system. If my recirc pump is not operating, the water that is stagnant or dormant in those pipes and the potable going to the fixture, that water is not moving and it's losing temperature. And when the unit gets a call for heat, there is a process, a pre-purge, a lighting off, stabilizing the flame before we start delivering hot water. So you get cold water going out, you get a source of hot water then, and then it's surrounded by another slug of cold water after it's all off. And we call that a cold water sandwich. Well, to counter this with Combi, we have what's called a Combi preheat function. And it's very interesting. The Combi preheat function keeps that boiler and the braze plate heat exchanger at a predetermined temperature. And this is completely adjustable. So the boiler runs at a minimum firing rate to not only reduce cycling, but prohibit that water from cooling off in the line, provided that it's in harmony, it's in sync with that recirculation pump. So this reduces that response time of delivering hot water to the fixture, and this is a very valuable feature. So that Combi, as opposed to the tankless, can stave off these types of issues and address that fully. I think that's very important. Now, moving on, water chemistry is a very important topic, whether it's on the space heating side or whether it's on the potable side. water chemistry is a big deal. And I was flying out to Vegas a while back, and as I looked down the the prominent dam that's out there, Hoover Dam, the water level was going down, and this residue was left. You can see where the high water mark was. Well, that residue is actually calcium and magnesium. Those are hard water deposits. And where do you think those hard water deposits are going to end up? Well, they're going to end up in a tank type heater, a tankless heater, as well as a combi. So we need to talk about what are the parameters for each of these units. It was very illuminating to me that with a tank type under-fired heater, there really are no parameters. You won't open up the manual for our Lochinvar water heaters, and you won't see a minimum grains of hardness or TDS, total dissolved solids. The only parameter is that it must meet the verbiage that EPA has defined as potable water. As long as it conforms to the potable water as defined by the EPA, there are no minimum standards of water chemistry for tank type heaters. If you do some due diligence and some legwork online, you look for maybe Google water chemistry for tank type heaters, this is what you will see. You will start to see these third party or ancillary items that will illustrate and show you, if you pipe them in with the heater, how you can extend the life. In other words, it won't lime up and heat up and scale up as quickly. So these are very interesting. So the widest or the most generous of these in comparison would be the tank type heater, because there is very little, if any, water chemistry parameters. Now, to a tankless water heater, it becomes a very real. Remember, these tankless heaters do not hold a lot of water. So unless we're moving that water through at a very high velocity, we have to look at the minimum and maximum grains of hardness. 7 grains of hardness is our maximum in a residential application. 4 grains of hardness in a commercial application. If we're beyond that, we need to bring softened water or conditioned water into that tankless heater. Also, in a tankless, you will see defined a pH. These are the minimum and maximum parameters for tankless water heaters. It also goes on to state in the manual that well water must be treated. So tankless has some very clearly defined water chemistry parameters. And again, you can also deploy those same types of devices to provide conditioned water to prevent them from scaling up. And then on to the combi, and it gets a little bit more involved as it pertains to water chemistry, because we have 2 sides of that heater. We have the boiler side, and then we have the potable side. So we have some very real parameters here, between 5 and 12 grains of hardness on the boiler side. And then on the potable side of that brazed plate exchanger, the same was true with tankless heat or tank type heaters. It only has to meet the requirements as defined by the EPA. As long as it passes that, it's absolutely fine to run it through the domestic side of that brazed plate exchanger. And then on to total dissolved solids. We have very clearly defined parameters there. So a very defined bandwidth of water chemistry between tank type heaters, tankless heaters, and combis. So not only on the potable side of a combi, you're now starting to see the saturation in the industry of conditioned water on the fill side. Now, Bob, you're welcome to interject here, but this is a fill valve. So as that, on the space heating side, as that air heat, or as that system fluid heats up and the air, entrained air leaves via the air separator, we need to replace that volume with more water volume and a constant fill pressure. So the fill valve not only reduces pressure from your city main, it maintains a constant fill pressure and keeps that static system pressure at a constant level. Now you're starting to see these devices provide conditioned water. Any water that enters that system will now be conditioned. And Bob, you can sure add in whatever you want to at this point.
No, you're doing a great job. Thanks. That's exactly right. That's just to additional fill water. Obviously, you want to fill the boiler the first time with good quality water, either on the job site, demineralize it, or bring some water with you if you have water that's outside of that spec. And this is just a little replaceable cartridge unit that we offer just to go on the fill water for, like Paul said, any water that would leak out or air that would purge out that would need to be replaced. This will just assure that makeup water is also conditioned. So thanks for the plug, Paul.
Absolutely. And then on to controls. Again, with controls, we range from mild to wild here, from simple to a little bit more involved. And a tank type water heater is a very analog control. And with that, the dial programming, you're getting your hot down here, A, B, and they have your gradients in there. And there are some temperature scales that can tell you approximately where those are going to wind up. Safeties, relief valve, emergency cutoff, anode. One of the questions that came up was what is really new and innovative as it pertains to safeties on tank type heaters. And with the new ANSI standard, you see this flame vapor ignition resistant burners that have entered the market. These have been out a few years. This shouldn't surprise anyone, but these have done a very good job getting us to a point where if some liquid or combustible was to be nearby or splash onto that surface, it will provide an emergency cutoff. So again, a lot can be said about a 20th century technology, but now with 21st century safeties, even on a very modest tank type under fired heater. Moving on to tankless, we get a little more sophisticated with the digital control, some alphanumeric codes. We do have some flow sensing. Again, we're adjusting flow, sacrificing flow to meet set point. There is an air-fuel ratio sensor, a fair level of sophistication that's monitoring the combustion going on within that tankless water heater. So it's pretty sophisticated now. But just remember, we're also what's always going to be true is the higher the temperature rise, the lower the flow rate. And that modulating valve is going to back off and restrict flow so that we can maintain set point. And that is a fair level of sophistication, I would say, and controllability. And again, a modest amount, a very great amount of safeties here as well, an appropriate amount of safeties. One of the questions was that came from the audience is, can I use a tankless water heater as a boiler? Well, that is a loaded question, and it's not. The answer to it would be yeah, but if you look at what that heater was designed to do, that tankless water heater was designed and certified under this ANSI standard right here. So ANSI Z2110.2. It has a different set of criteria than what the boiler was designed to do. So the performance from each of these appliances was completely different, and the standard they are testified and certified to are completely different. So a tankless water heater really handles higher pressure, moderate temperature, and wider delta T's. In other words, a pretty high temperature rise. The boiler, on the other hand, is the opposite of that, a little bit lower pressure, lower temperatures, and a much narrower temperature rise, or a narrower delta T through that unit. So that is a loaded question. That's for you to decide, but you know, I'm tempted to use the analogy of buying a Ferrari, getting in the Ferrari, pushing the accelerator to the floor, and then using the brake to control the speed. Well, I can do that. It's just not really what it was designed to do, but yeah, absolutely you can do that. And I guess I understand that's a bit of an exaggeration, but look at those appliances and what they were designed to do, what they're certified to do, and move forward responsibly from there. Responsible design is important. And then on to control with the Combi, a fair level of sophistication, plain English programming, digital. We can sequence up to, 8 units together that will function and rotate, lead lag, so we'll get equalized runtime between all of these. One of the new things out there with the Combis is we're basically electronically derating it for space heating load, and that's a lot of fairly technical verbiage, but what that's essentially saying is, look, I've got a 199,000 BTUs available on the chassis of that appliance, and I want that full complement of BTUs, 199,000 BTUs per hour, for my domestic water production. But on the same sense, on my space heating side, if I've done my load calcs or a heat loss, maybe I only need 80,000 BTUs of those 199,000 BTUs. I can electronically derate that appliance to say, look, when a space heating load is applied, only fire to 80,000 BTUs, or whatever that percentage firing rate is. But yet, when the domestic water calls, give me that full complement of BTUs. So a fair level of sophistication here. We talked about that domestic water preheat on the Combi. These are all important. And again, fair number of safeties as well. So again, we go from analog to digital and anywhere in between as it pertains to controls. Service is a very difficult topic to really do in a modest amount of time. But if you look at it in a side-by-side comparison, again, I'll illustrate an electric water heater here. This is gas-fired with a burner. Electric water heaters have elements and some thermostats here. But then you look at the plenum of a tankless water heater and the plenum and serviceability of a Combi, and to do a side-by-side comparison, you look at the number of components, the ease of accessibility. Really, if you look at a tank-type water heater, the market is saturated with these parts: a relief valve, the burner, the gas valve, which has the built-in emergency cutoff, dip tube, anode rod. There's a really modest number of parts, and your access and ease of service, I'd say, is a pretty tremendous thing. I think it gets the tip of the hat in this instance in that side-by-side comparison. Moving on to a tankless water heater, it becomes a little bit more involved. It's not an impossible task. Obviously, these are intended to be serviced. But there's your list of basic service items. Or filter. You're going to look at the venting and combustion air. You're going to go through all this list and potentially de-lime that heat exchanger. Again, if you've got aggressive water chemistry, you're going to need to de-lime that heat exchanger. And based on that installation process, if you go ahead and install these types of service valves, it makes that de-liming process very, very quick and simple. So again, very easy to navigate and service. Look at the architecture and the area where your hands are going to be, what components you need to replace, and you can make your own decision from there about serviceability. A little bit more involved than a tank type heater. Now on to a boiler. Again, you've got one appliance functioning as both space heating and domestic water, so we've got to look at both sides. We're going to look at that same items. We're going to service and clean the combustion chamber, gas pressure. Hopefully there was a combustion analysis done on it when the boiler was set up. On the potable side, you can de-line that heat exchanger. What's been interesting is, and what we've seen happen is, on the back side of these brass valves, that's where that braze plate heat exchanger is. And if you were to loosen and remove these two Allen screws, that basically disengages that braze plate heat exchanger. The posts on the back side of that are not NPT thread or male pipe thread. They're basically posts with O-rings. So it's self-sealing at that point. So just by loosening these two screws right here, you can remove that braze plate exchanger, de-lime it, maybe take it back to your shop and de-lime it and put a new one in and just continue to replace them, manage your time very well. So that has been a new feature. You can de-lime them just like you can a tankless in place. But again, serviceability and navigating that architecture is very simple. We're very proud of lochinvaru.com. It's a separate website, forward-facing. You can navigate to lochinvaru.com, go to the instructional videos, and you can spend 4 or 5 minutes. Learn how to service, access, and clean that combustion chamber. How do you do a combustion analysis? Very granular, very digestible videos on how to service this appliance. So I think in terms of serviceability, getting in and out of the cabinet, we've made it as simple as possible for a Combi boiler. Now we're getting into a very subjective area where this was requested as a side-by-side comparison. The request was that we look at these 3 questions, cost-wise. Tank type versus tankless versus a Combi. Is that a wash these days, yes or no? How about an honest no sales comparison? Well, I'm going to do my best to be transparent here. And then finally, when does a Combi heater make sense? So moving forward, we know this is a completely subjective topic. There are differences from one contractor to the next as it pertains to overhead. There's code body issues, whether international plumbing code, uniform plumbing code. There's regional differences in terms of pricing. So knowing that, I'm just going to ask for your patience moving forward. So in this narrative addressing cost, we have our first tank type water heater. There it is, 40 gallon, 40,000 BTUs. In an installation, if we were to replace it, if this was what was installed, if we were to go in and replace it side by side, a cost that came to me. These were all generated from a very responsible, very well-respected contractor in the industry. That contractor, knowing they didn't have to rework any venting, my ancillary costs, and maybe if they wanted to add a mixing valve, or if there were fittings involved, plus or minus, that might have a bearing on these costs. But a basic middle of the road, like for like replacement, they're suggesting an $1,100 price. And I know this is very subjective. The efficiency rating with that is the UEF. Now, this might surprise some of you, but the industry has really shifted. That UEF is the uniform energy factor, and this is now the new metric that replaces the older EF rating. You used to just see an EF rating. Now you will see the UEF rating, uniform energy factor, and it's at a 0.65 on this unit. Moving on, here's again where we want to clearly define what's going on in that market. If that end user, Mrs. Jones down the street, wants to yank out that 40-gallon, 40,000 BTU heater and replace it with a 199,000 BTU tankless water heater, this would be an indoor model, 199,000 BTU. That moves us up to a Cat 3 venting. You allow plus or minus $200, plus or minus 2 hours of labor. This would be a suggested replacement cost. It becomes a little bit more involved. And with that, you get an 80% UEF rating with that indoor non-condensing model. Now, just to be clear, we move on to a Combi. That Combi would then not only provide space heating, but it would provide domestic hot water. It's again 199,000 BTUs. It modulates, it condenses. That condensing operation then moves us up to a Category 4 venting, AL294C, polypropylene, CPVC, PVC Schedule 40. This is going to be plus or minus 5 to 10 hours reflected into this cost. So again, very generic, very simple costs. But again, with that, you're getting very high efficiency. Now, having said that, this is a condensing appliance. And what does that really mean is, if my entering water temperature into that boiler is low enough, those flue products will reach their dew point, they will condense, they'll turn into a liquid, and that condensate will roll back down that heat exchanger. So the lower the firing rate of that appliance and its ability to modulate, and the lower the entering water temperature, the higher the efficiency of that appliance. Now, that can also then be applied to a condensing model for a tankless heater. To be fair, I used a middle-of-the-road indoor non-condensing appliance, but absolutely, there are condensing models available as well. So as a apples to apples or side by side comparison, this will just show you the scenario. I'm staying away from the verbiage of good, better, best. We're going to let that end user decide what's going to best serve their needs. When, again, addressing that, when does it make sense to change out or change to a Combi? Well, one of the scenarios that might play out would be an old boiler that has a tankless water heater, or rather a tankless coil in it. So that appliance has a fair amount of water. Typically, there's a cast iron sectional appliances. It has this tankless coil in it, and that's where that potable water lives. So that boiler has to stay hot 24/7 and be ready for a demand of domestic water through that coil. If you're replacing out a Combi boiler for both space heating and domestic water production, this then becomes a natural fit for a Combi. Another operation or another instance application, as it were, would be a conversion where you have a boiler for space heating and a separate tank type water heater for the domestic load. If you're changing these out, maybe you replace the boiler and hook up your space heating side, and then eventually when the domestic fails, you bring that piping over to the Combi. Now you've got a 95% efficient appliance in a singular chassis that is going to do very good things for you. So it depends on the application. This is a very nice job from Quality West. Spoke to this gentleman yesterday. We're really glad to have him on board. This is a really nice quality install. Caleffi air separator there, Caleffi fill valve, pressure reducing valve, and fill valve there as well. Now, finally, we're getting into the final few slides here. We're doing pretty well for time. But to be completely transparent, side by side by side, I don't want this to be a gradation, but essentially I have to go in and say, look, someone should get the nod with a single check, 2 checks, or 3 checks. So if you look at cost, we just reviewed pricing, that tank type heater replacement was the least expensive. So if this row is a large driver, this could be a very weighted row right here. My Combi was the most expensive in that replacement market. This is how we should score it, if you will. I don't want to use the word score either, but we have to look at each of these for their own merit, because end users might have different things that are important to them. In terms of DHW production, what we saw was first hour recovery with that 40,000 BTU heater was 78 gallons per hour. The tankless heater was 252 gallons per hour at that 4.2 GPM flow rate. And then that Combi was capable of 4.8 GPM or 288 gallons per hour. So in a side-by-side comparison, they function completely differently. Applications. Again, the Combi, the singular chassis, can provide both space heating domestic water. We talked about using a tankless as both a heater or a boiler. Again, certified for design to do different things. Again, same thing is true with a tank type heater. Serviceability, we give the nod to the tank type heater. There are fewer parts. Ease of accessibility, it should get 3 check marks. The Combi, in terms of ease of navigation of that cabinet, replaceability, number of parts, I think this is a fair representation. Again, completely understand that this is going to generate some commentary out there, and I'll be glad to face this head on as well. Water chemistry, that tank type water heater had the least requirements. We only had to meet the EPA definition of potable water, so very non-restrictive. The tankless had the greater number of and smaller amount of hardness parameters and TDS parameters at 7 grains of hardness as opposed to 7 to 12 grains of hardness on my Combi. So again, looking at water chemistry parameters in that scenario. Efficiencies, again, this is very weighted, the UEF number versus that efficient. And again, I realize and fully accept that we can get some tankless heaters that can get pretty high efficiency as well. Along with that, I will say, look, these were designed by the respective ANSI standard. So the design criteria was completely different for each of these categories. So again, we got to know that that's the elephant in the room here. Finally, in terms of controls, we went from analog to digital and everywhere in between. So in terms of programmability and functionality, yeah, that Combi is designed to do a great deal of things. So I hope you will agree that this is fair representation. This is not a good, better, best, because I fully realize this first row right here might be the biggest barometer, the biggest single driver of what that replacement market might look like. So that really moves us forward to the end of that presentation. I know we've chewed a great deal here. I'm completely open to questions as time allows. You're more than welcome to email me at prohrs@lochinvar.com. I will be here for the duration, and again, we'll answer questions as we move forward.
As it relates to producing domestic hot water, when you're using either a tankless or a Combi, a question came in, what conditions can cause the delivered temperature of the water to either be higher than set point or lower than set point?
On the, well, okay, so on the boiler side, or even on the tankless, or the Combi or the tankless, the Combi allows for a set point on the potable side of up to 180 degrees. The reason we allow that is maybe we do want to use that mixing valve. So in terms of that hot-cold mix principle, if on the boiler side I can produce through that heat exchanger and send on the downstream side of that potable heat exchanger through that anti-scald mixing valve that we saw that animation on, if I do the hot-cold mix principle, I can extend that water volume. So absolutely, I can have a higher water temperature on the upstream side of that mixing valve than my delivered water temperature. And I think we can say the same thing on a tankless water heater. We can dial it up to provide a 140-degree delivered water temperature out of the tankless, but then mix it down to a respectable, anti-scald mixing valve that would then give us a delivered water temperature. So those would be two that I can think of that would very easily have higher temperatures on than the delivered water side.
Okay, great. Thanks for that. You mentioned, I think earlier, the term line of demarcation. Was that the term? As it relates to the number of tankless. When we train on solar collectors, we kind of use the same term that you don't want to exceed 6 solar collectors when you talk about flat plate in an array, because anymore you start starving the internal risers, the ones towards the middle of flow, and therefore it's more of a performance line of demarcation. I think you were using the term line of demarcation just to clarify, as it relates to the number of tankless in a commercial system. That kind of the rule of thumb makes sense. You said 4 to 6. It's not from a performance issue. You can put together quite a few in parallel, but it's more of a financial issue. Is that what you were talking about?
Absolutely. It's not about the inability of a tankless to produce the total domestic load. Absolutely, it's possible to do that. But from a first cost standpoint, that was what I was referring to as it pertains to the line of demarcation. If I get 15, let's just pick a number, 15 tankless water heaters, and I successfully install them, they meet the load. So what is the installed cost of each of those units with the gas piping, with the venting, with the annual service every year, compared to maybe 2 smaller heaters and 2 storage tanks from a first cost standpoint? So in those instances, that is for the user to define. What is that line of demarcation that makes sense from a first cost standpoint?
Great, thank you. On recirculation, hot water recirculation, do you have experience in terms of any issues to be aware of when you're recirculating hot water, when your source of hot water is a tank type hot water heater versus a tankless? Any kind of rules of thumb or things to consider for the contractors?
Honestly, I'll invite Bob to pipe in on this. Well, I don't know of anything that would be different other than what you've seen. I will say that proper check valve placement is always a concern for proper operation. Also, with expansion tank placement, making sure that you place that check valve so that you don't isolate that expansion tank. We still need that hot water. As it heats up, it expands in volume, roughly 2% per 100-degree rise. So we have to have proper placement of the check valve, proper placement of the return, proper placement of that expansion tank to get a very thorough and responsibly designed recirculation system. So I don't know that I can add any more than that, and that's very normal. We've seen this in the industry in days gone by.
Yeah, thank you for that. Yeah, speaking of those important check valves, a common misconception is that if you have a check valve on your recirculation, if you have a commercial system where you have a number of circuits that you're recirculating through, in addition to the check valve on your main line, any risers going up to your fixtures, they also need to have check valves to prevent some strange things that happen temperature-wise in your risers. So not just the main circuit. So.
Yeah, and thanks everybody for supporting Caleffi, and as always, let us know what we can do to help you. Any products that you have on your mind or anything that we can write about in hydronics or talk about on future webinars, we'd love to hear from you. And I want to thank Paul again and Lochinvar for loaning them to us for this presentation. They did a great job covering all this information, and I hope everybody has a Merry Christmas and Happy Holidays, and we'll see you again in January. John Siegenthaler will be here. He'll also be at the ASHRAE show. Come by and see us. Anything else, Paul?
No, but thank you. I appreciate it. And on behalf of Lochinvar, thank you everybody for tuning in.
All right. Thanks, everybody. We'll see you soon. Bye-bye.
All right. Take care.